All right, so we'll just jump into it. So I'm going to introduce the speakers here. I'm the unfortunately only in-person representative of the AFLOW team, but I'm very fortunate that they were able to join over Zoom. So my name is Oses. I'm an assistant professor here in material science and engineering, and I'm joined by David Hicks. He was a postdoc with me at Duke, and now he's working at Lift Technology. He's a principal engineer there for modeling and simulations. I'm also joined by Hagen Eckert and Simon Develov, both of whom are postdocs at Duke. And we've all put in a great deal of effort and code into the software framework AFLOW that we'll be discussing today. A lot of the work that will be shown today would not have been possible without a giant list of collaborators, all part of the AFLOW consortium. So I just want to acknowledge collaborators at Duke, NC State, Central Michigan, University of North Texas, University of Buffalo, St. Olaf, UT Austin, Penn State, UCSD, Carnegie Mellon, UNC, University of Maryland, and even collaborators abroad. All right, so we got this full schedule today, starting off with coffee and pastries. I hope you're able to enjoy. Feel free to help yourself to more. We have plenty. We'll be starting off with a brief introduction, just introducing AFLOW and what it's used for, what the community has been using the software and the database for. Then we'll quickly jump into the machine learning session, talk about a number of models that we use, materials informatics. Then we'll follow up with a session on crystallographic tools. So this is symmetry analysis, structured prototype generation, our encyclopedia of structures. We'll take a quick coffee break, and then we'll transition into a talk on the database and application programming interfaces, and we'll conclude with the discussion on thermodynamic stability and associated analysis. So quick notes. So we should have we can organize, if we don't already have it, a breakout room for support. This is really more for the people on Zoom. If you have any issues with Zoom, Binder, exercises, I think the best way, especially for people here, is to just shoot a message to anyone with an AFLOW organizer under their name, any of the co-hosts. So if you have any problems here in the room, we also have Keith Clark, who's becoming an expert in AFLOW. He can help out. So if you have any questions, feel free to ask Keith about ask him anything on AFLOW or these associated exercises. All right, I'm going to pass it over to Hagen now. He has a nice setup for our exercises today that he's created through Binder. Hagen, can you
sure.
Pick it up?
Everyone, my name is Hagen, as you heard already. Today we will show you some demos and exercises that will utilize Python and some fetching resources from the web. While we don't have a lot of time, we made all of these exercises available for you so you can kind of play along with us. The easiest way to go is you got an email before with the slides. Every time when we go to an exercise, there will be a QR code and a link you can simply click to go there, and the worksheet will open up for you and you have your own environment. Even after this course is done later, if you want to revisit it, you can use the links or go to the GitHub page and actually look at all of the examples, and over time also more examples from future schools. Could you go one slide further? Thank you. So if you click these Binder links, you will directly go to an open notebook. If you want, you can also do this right now. On the left side, there's the little folder icon. There you can switch to different exercises if we go to new ones, or you can just then click the new links in the slides itself, or just scan the QR code with your iPad if you want to. Again, most of the exercises we will walk you through today, so don't feel scared. But if you want to click along, open the notebooks. Yeah, that's mostly it. Should just work.
Yeah, and Keith will be pasting into the chat the links for the slides and also the exercises as they come up. So just watch the chat and click on the link there if you want. But you should also be able to click in QR code and all that right with the phone if you want to see it there. So Great, thank you, Hagen. All right, so we'll jump right into it. Okay, so materials development, there's a few different variations of materials development. I want to orient what we mean and the kind of work we're doing here. So there's what I call the traditional approach of materials development. We start off with a set of materials that are generally naturally occurring, materials that exist in nature, naturally occurring, and we can take them and we can characterize them for their properties. Okay, so iron is magnetic, copper conducts electricity, and we can analyze it for its mechanical properties, catalytic properties, so on and so forth. And based on that set of properties, we can engineer them into a set of applications, right? So electric motors, if it's magnetic, electronic circuits, if it conducts electricity, so on and so forth. This is a very passive approach. You can sort of jokingly think of it as Deus Ex Machina, if you're familiar with the movie reference. It's almost as if we're waiting for the solution to fall from the heavens. Okay. Now there's another approach that's much more active. We start off with the application in mind. Let's take catalytic converter as an example. We know that we need high temperature functionality. We need good catalytic activity, probably nice mechanical properties. So we take that set of properties and we look for the material that optimizes that set, whether it be naturally occurring and known or a hypothetical structure. So you might be asking, what is a hypothetical structure? A hypothetical structure really means that it has not been realized in experiment yet. We don't know if it can form under the conditions that we have here on Earth, or that would be operating under the conditions of the device. So how do we form these hypothetical structures? Well, one of the ways that you can do so is you can draw inspiration from nature. Both nature as in nature out there in the world, but also nature, let's say, from the journal. So here we have a structure that's been reported in the literature. It's a half-Heusler structure, well known, well characterized. It was founded in World War II. It has a particular composition and a set of arrangement of the atoms. Okay, we can actually extract out the backbone of that structure, okay, for an arbitrary composition, and we can redecorate that structure with different components here, different elements, and we can calculate their properties. And we don't know if these exist, if they're going to form, but we can calculate that. And we can actually characterize these materials, at least computationally. So this forms under the prototype encyclopedia, which is a project that's been going on for a long time. We have a number of parts here. So it started off in 2017, formally with AFLOW, and it began even further back with the Naval Research Laboratory with Mike Mell. Now we're at about 1,000 different prototypes and growing. And it's not just as simple as digging through the literature and trying to figure out what new structures exist, because there's a lot of structures that are reported that have already been reported or existed. So it requires really an intimate understanding of the symmetry, the structure, the Y compositions, and like David's going to cover that in detail later. But it is quite a challenging project. So we have our prototypes here. You can imagine that we can decorate these with all the different combinations of elements in the periodic table. But this is not a combinatorics game you want to play. This number is actually larger than the number of atoms in the galaxy. Okay, so it's a really big space. And the point is that, if we wanted to synthesize these materials by trial and error with experiments, each one of these experiments could take days, weeks, months. Depending on the approach, it can take a long time. So we need a framework, something that can accelerate that development, and then we can explore these spaces faster. That's where AFLOW comes in. So AFLOW is a computational framework. Well, it's really two parts here. Okay, so there's the C++ software framework, and then there's the AFLOW repository. So AFLOW began roughly around 2000, 2003. It had its beginnings, I would say, in two parts. So it really began roughly as a wrapper around density functional theory code, which is so density functional theory is a way of analyzing the electronic structure of materials. And then AFLOW is also the code, the software, the way the community was using it was to derive the Brillouin zone standard representation. So this path that we follow in the Brillouin zone, we're not going to talk about too much in detail, but this was standardized by AFLOW. Okay, so the code offered the way of calculating that for your particular material. But now it's become a full autonomous materials framework. Everything from the input file generation down to database storage has been automated. Okay, we can calculate a number of different properties: electronic, vibrational, elastic. We'll talk about a few of those here. Then this code has generated what is now the largest database for inorganic materials. The repository contains 3.5 million materials, each characterized with hundreds of different properties. So we have over 700 million properties in total. And we have a lot of different ways that you can interact with that data. Different modules for machine learning, which we'll cover in a few minutes, structure generation, stability, and formability. We'll talk about those today. So this concept of predicting a material that we don't know if it exists, handing that list over of candidates to an experimentalist, and then them realizing the material and the properties that we predict, this ab initio discovery, it's very challenging. And it's even more rare in fields of technological significance. And we've had quite a bit of success in that space. So I'll give you a few examples. In 2017, we discovered 2 new rare earth-free magnets. These were the first magnets discovered by computational approaches. Now, why rare earth-free? Well, magnets are everywhere. They're fairly ubiquitous, but there's actually only a few different compositions that can realize a magnetic state. Most of them are rare or have some sort of rare earth in it. Despite the name, rare earth is actually not that rare, but they're difficult to mine, and they're generally isolated to particular regions of the map. So their prices are governed by politics and the general status quo. So we want to move away from rare earth magnets. In 2017, we also discovered cobalt-based superalloys. Most superalloys are nickel-based, and they're important for the engines of airplanes. They have very nice high-temperature mechanical properties. We offered a number of candidates in 2017 for publication, and then in 2018, an experimental group independently verified 2 of those predictions. In 2018 and in 2020, we've had success in the space of high entropy ceramics. This is really where our research has been really blossoming in this direction. We see them as being the evolution of superalloys for the next decade. If you think about hypersonic vehicles and other applications, but we work really work that we've done has been largely in the carbide space. Finally, in 2020, we helped discover a new phase change memory composition. What made this work so exciting was that the whole process of discovery was driven by a self-driven lab. Okay, so we had robots and people and they were working the experiments, and so they were querying our APIs for information about building up a prior for the machine learning model to understand where to look in the phase space and what decision to make next. From an application standpoint, why these are important. So everybody knows Moore's law with this geometric relationship for CPU performance every year. We should be getting better and better CPUs. What's often not talked about is the lag in memory performance. And so we need these types of materials to bridge that gap. Okay, so I alluded to this already. The challenge is the giant material space. We need a way of guiding ourselves blindly in the dark here with this giant space of possible materials. Now, another challenge is that there's only of this giant space, there aren't many that we expect that are going to be interesting to us, depending on the application. Okay, so the idea I want you to keep in mind here for the rest of the talk is this is kind of the general approach of how we go about materials discovery. Think of this funnel here. Okay, so we start off with a set of a piece of this material space. Maybe we pick a particular structure prototype and we decorate them with different compositions. Maybe we have a set of structures we're interested in and a very exclusive set of components, right? Depending on the application, we have some large set to search. And then we start to funnel down candidates. So one way we can do that is by analyzing stability. We will talk about how we calculate thermodynamic stability. It's going to be important for the particular conditions under which the device is going to be operating. We can also calculate mechanical stability. We won't be talking about this too much today, but we want to understand if there are modes which are realizable that will yield mechanical instability. And then there are, of course, application-specific criteria, right? So if we're looking at superconductors or magnets, we want to optimize their respective critical temperatures, right? The superconducting critical temperature here, the Curie temperature here. If for superalloys, we looked at two-phase equilibrium between the precipitate and the host. That's very important for precipitate hardening, and if you have experience in that. And then for thermoelectrics, the figure of merit is something you want to optimize, or associatively, the lattice thermal conductivity. So this funnel is a very important idea here for how we realize the functional material of interest. And with that, I'm going to conclude with the introduction. If anyone has any questions, otherwise we'll move in quickly into the machine learning aspect of the talk and the associated exercises. Any questions? No. All right, great. Go ahead.
So does this deal with test materials at crystal level?
So crystalline materials. And I would say that that is the primary set of materials that we work with, basically because of the theory. But there we have models we have ways of modeling both chemically disordered and amorphous structures. So things like glass. So we won't be able to talk about the chemical disorder here. It looks very exciting. This is for that high entropy space. That's exactly what we're working with. And Hagen, again, we're not going to be talking about too much, but Hagen also works a great deal on metallic glasses, for instance. And so we have ways of doing that. You can model it based on crystalline structures, or ways of understanding disorder based on crystalline representations, let's say.
But most of the time you're dealing with things at atomic scales or molecular scales.
Right.
Not the scales above. Like in the same book that the scale flow might have presented PF and other things.
Right.
Right. So
yeah, you're asking if we're more continuum, if we go at that level. Yeah, AFLOW is really working primarily at the DFT level, though we definitely have interest in going, let's say, in the direction of molecular dynamics and automating processes there. Yeah, absolutely. That's definitely an interest. But DFT is going to play an important part in that role. It's going to continue, right, making interatomic force fields and the like. So it's all part of the progress of moving forward. Yeah. Any other questions? Okay, good. So we'll pick it up with machine learning and material science, the AFLOW-ML module. So keep that rung and that filter, that cone in mind. But the challenge here, or really, I guess, the objective first, is that the idea is that we have a lot of data already, whether it be experimental, computational, and we want a way to recycle that data so that we can accelerate discovery. Okay, so each rung of that funnel that I showed you is going to require at some level at least one, if not many, DFT calculations per material. Okay, there are some properties, like the thermomechanical properties, that can require 20, 30 different DFT calculations. Each one of these calculations can take days to weeks. Okay, so each rung is going to be very slow. We want to know, is there a way that we can go through each of these rungs faster? Now, it's not only is it costly to calculate, but it also requires a very nice computing environment. And so it's really sort of a specialized type of calculation. So we want to be able to build a model, construct a model that can predict these properties, and we can get these predictions faster. It's something that maybe you can even use, let's say, on your computer, which you'll be able to do today to run these models. Now, on the machine learning end, these models are going to be built off of, it really requires a specialized knowledge of what you're doing, right? So you need to understand the algorithm, whether you're running random forest, partial least squares, neural networks. You need to have an understanding of the algorithm. You need to build the software, so you need to have some coding experience. You need to have plenty of data, and you need to have a firm understanding of the applicability domain of your data set, right? So your data set isn't going to cover all the possible, let's say you're trying to predict band gaps. It's not going to predict, maybe your data is really focused in on a particular range of band gaps. Well, don't expect that model to be able to predict something that has a super high band gap. So you need to have an understanding of where your data is and what it's going to be useful for in terms of building the range for your model. So we want to build up tools basically that abstract away a lot of those details. As long as you understand what the model can give you in terms of properties, then you can just use that and incorporate that into your framework. So we're going to go ahead and we're going to navigate to AFLOW.org/AFLOW-ML. If you want to type that into the chat so people can just click on it, that would be helpful. So you can actually navigate it also from the AFLOW website. You can scroll down and you click on the AFLOW-ML app there, and it'll bring you right to the web page. There's a few different ways of accessing it. Ultimately, you'll arrive at a page that looks like this. I'll give you a few minutes to get there. Everybody able to? Would you mind muting them? I don't know who that is.
Yeah. Maybe one of the co-hosts can do it.
Oh, okay, yeah, well, can one of you guys try to mute that? I don't know who that was, but anyway, so, okay, so here we have our models, okay, so, again, I'm not gonna go into a whole lot of detail of the technicalities here. The goal is that you don't even need to know that at some level. Of course, if you're, if you're gonna want to understand these details in a more intimate relationship, if you're actually working with them for discovering new materials, but really, just for our purposes here, we're gonna be talking about 3 different models that can offer a few different sets of properties. Okay, the first one is called PLMF, which stands for Property Labeled Materials Fragments. And you can see here that it offers electronic and thermomechanical properties of crystal. We have the MFD model, the molar fragment descriptor. This is going to be vibrational properties of a material. And then we have the ASC, which is the AFLOW superconducting model, and that's going to give you the superconducting critical temperature. Now, there's a little set of instructions here for those of you that want to follow along. You can just hit got it, but otherwise you input your structure here, and I'll talk about what that means in a second. You input your structure here, you hit run calculation, and in a few seconds, you should be able to get a prediction. So you can run that now, but I'm going to quickly go through the format for our structure file, just for those of you that are not familiar with, let's say, VASP or what a structure file looks like. So here we have a simple example of a face-centered cubic aluminum. Okay, so we have a face-centered typical FCC structure here. Which is built of 2 components, right? All crystals are characterized by their lattice vectors and then the basis atom, the basis vectors for the atoms. So the lattice vectors here, we have one, we have our lattice constant, and then we have each lattice vector along X, Y, and Z. Okay, so that's going to define our orientation here. And then we have our basis of atoms. We have 1 at the origin, and then 1 at basically half steps of all the lattice vectors. Okay. So that's how we build our structure file here. The first line here is just a comment line for what the structure is. We have our scaling factor. Here we have our lattice vectors, A, B, and C. Okay, so you can see how we X, Y, and Z built in like a matrix. Here we have a line that specifies the species, aluminum, and then the number of atoms. We have 4. I showed you that earlier. And finally, we have our lattice vector, our basis set here of atoms. And we specify the coordinates based on the direct coordinate, which is based off of the lattice vector. So we have half and half based on half of the first lattice vector and half of the second lattice vector. We take the sum, that's where the atom should be. Okay, so that's how you specify the coordinates of the atoms. So just a quick note, this isn't too much of relevance for you, but at some point we had a transition from VAS4 to VAS5. The only difference in the structure file is that we need to incorporate the species, which I already told you. So it's not a big deal. You won't need to worry about that for the session. So yeah, if you want to go ahead and navigate to AFLOW.org, I'll do that with you. I'm going to stop sharing very quickly. And I'm going to pull up the share desktop. Okay. All right. So if we click on AFLOW-ML, smaller, okay. All right, so we hit got it. We go here, we see that we have an example structure here, so you can now hit run prediction. And if you scroll down, you give it a few seconds, you're actually going to get a suite of different properties. So the PLMF model offers electronic and thermomechanical properties. So it's going to tell us metal insulator classification. It's going to give us the band gap. It'll give us the energy, the bulk, the shear modulus, the heat capacity, the by temperature, and thermal expansion. And below that, we also have some calculation details about the data which was used to build the model, right? So these are vast parameters that if you're not running your calculations at those parameters, you should not expect necessarily good alignment for the properties. So that's that first model. For the second model, we can use the same structure input and we can hit run prediction. And again, this one works a little faster. It's really built a lot on the composition. So we get a suite of properties, including heat capacity. You can compare that with the PLMF model, vibrational free energy, and vibrational entropy. Okay, and these models, they have associated papers where we validated them on a big suite of different materials. Finally, we're We're going to click on the AFLOW superconductivity module. And we're going to hit, so this actually does not take a structure file, it takes a composition here. Okay, and so there's an example there. You can go ahead and run prediction. This one takes a lot longer to run. I'll explain briefly what's going on. So with the model, what we're looking to predict is the superconducting critical temperature. So the threshold of temperature at which superconductivity turns on. It's usually in the colder temperatures. Now, a detail that's important about this model is that we basically, in order to build the model to have very nice accuracy and prediction and predictive abilities, we needed to separate the data between what's called low TC and high TC data. Okay, now there's some issues with doing that, but that's a general consensus for how to separate some of these materials. So where you define that threshold between low TC and high TC can change the accuracy of the model. So some materials might work better for one threshold and some work better for another. We have a full analysis of where that's going to work best. But basically, you're going to get two predictions. And for the vast majority of materials, these numbers are not going to differ all that much. Okay. But I refer to the paper for more technical details. And we can also take it offline if you're interested. But those are the three modules. Any questions there? Everyone should have been able to run.
All this simulation you hear is based on the DFT, the DFT theory, right?
Well, so these two, yes, and then so they're built off of DFT data and validated on experiments. The superconductivity model is actually built off of experimental data combined with data from AFLOW. But primarily there's a database called Supercon. And they have a whole range of data for different compositions and relative and the respective TCs. So you can build these models in a lot of different ways depending on the data you have and the fidelity you have in that data.
Okay.
Sure. All right. So if there are no questions, I'm going to stop sharing, go back to the slides. All right, so we have a few exercises here just for you to run. So we'll take a few minutes just so that you can get acquainted with the module. So on the next slide, I actually just give you the structure file so you can take it from the slides, copy and paste it into your browser. Should be pretty simple. So using this structure here, you should be able to copy it in and run the PLMF model. We have some questions here. What is it, a metal insulator? What are the values of the bulk and shear modulus? So you can see that from the set of properties there. You can run the MFD model and see what properties it gives you. I already given you a piece of that information. And then you're going to want to take the composition for this structure. Okay, it's not just ALCUMN, but it's a count of the atoms, essentially. You can upload that chemical formula and run the ASC model. What is the TC that you get for it? And I say you got to be patient here. I also give you some additional structures to run with the PLMF and the MFD models. One that we know, for instance, is an insulator from experiment silicon. And then I also give you FCC aluminum, which we know is a metal. Okay, so you can test and see how well the model does there. For the ASC model, I'll give you some other compounds to try. So you can plug in these compositions in there and try the module. But otherwise, I'll give you a few minutes. I'll probably give you about 4 or 5 minutes just to run through yourselves, and we'll come back together and go through the examples.
I didn't register since I wasn't driving here. Could you forward me the link to the slides?
Okay.
If that's okay. You just pop on Slack or something.
Yeah.
Yeah, sure. Sorry. We'll paste them in the chat. Did you register? Because we sent out an email yesterday. Did you get an email yesterday from?
No, I know.
Oh, that's okay, no worries. Keith, would you paste the slides in so that, yeah, please paste it again? Oh, and the link? No, don't worry, absolutely. We'll do it again. Anyone else who needs the slides are gonna go up in the chat. Yeah, don't worry, you don't have to type in that structure, it would be too much to do. So just copy paste, should be pretty simple. Oh. Any questions? Did anyone have any issue copy pasting from the slides, or did it copy paste fine? Everything's fine.
I think we have to replace each segment.
Yeah, we might, Keith just told me about that, it's okay, so, yeah, if you can, you might even just be able to copy paste the whole thing and then reformat it a little. You just have to move some of the lines to become a line. But otherwise, I hope it's a little easier. We have to figure out a different way to copy paste it into it.
It's not strictly a postcard file, right? Because I noticed the elements at the end.
So that's a common line, VAST won't read beyond the third, so you can add whatever you want after that. A4 takes full advantage. of it. Sorry?
We don't need to add the comment.
No, you don't need to.
Hashtag.
No, it's kind of, that's kind of an A4 thing to add it at the end, because the A4s existed before VAST 5.
They need it.
Hmm?
Or these, like, I mean, need it.
The module, so A4 will understand, yeah, it'll understand the elements at the end. And it actually takes a lot of different format files, so Quantum Espresso, it'll take AIM, FHI AIMS, it'll take L code, the A4 can read and understand a lot of different structure types.
So, Corey, I have a question about the model. So one source of discussion about using DFT is basically the accuracy of the functionals. There are thousands of them. And what is even worse is that people can tailor the functionals according to the property that they are looking for. So basically fixing the results.
Yeah.
So I get what I want.
Yeah.
So how does it play in these machine learning exercises?
Yeah, that's a good question. So this is sort of a technical detail about DFT. For those of you who don't know, with density functional theory, there's a component of the theory, which there's a term in the energy series that is basically a garbage collection term, is what we call it. Basically, it takes everything that we don't understand, theoretically puts it into that term, and then theorists have come up with different ways of approximating what that term is. So there are a lot of different functionals that exist in literature, and a lot of them, as you said, have been fitted to the properties of interest. So there are some functionals. I don't know. I mean, you must see just as a different point on the side. There are some functionals that sort of satisfy very strict theoretical concepts like scan, right? So that's a nice development there. So using nice functions.
So yeah, it would have been lovely.
Raji, could you please, oh, no, he muted himself.
That's okay. So there's some nice functionals you can use, but I would say otherwise, you have to understand what functional you're using for the type of, I would say, types of materials and types of properties. So as a standard, we generally use the Paul PDE functional. And we have one functional we use that we understand that's very nice, generally for intermetallics, and we understand that it's going to work well for a lot of the properties that we've been working with. Now, it's not going to work well for everything. But that's what makes sort of machine learning interesting here, is that if you have consistency in your database, a lot of these errors can be fitted out, right? So if you train your data, if you train on a full set of POP-PV calculations, it's going to miss the band gap all in the same way. So you're relying more or less on trends there. And machine learning can basically do an offset there to, if you have experimental data, to complement it, you can feed it in that higher fidelity data, and you can offset it there. So that's what makes machine learning so important there. But I would say the most important thing about these big databases, it's often missed by some people, is that it really needs to be consistent. So all the calculations here, we have what's called the AFLOW standard for how we run our calculations. Is a very strict set of guidelines for what parameters we use for each calculation. And if everything is done consistently, machine learning is that's a nice environment for machine learning or for data analysis or the like. So as long as you have a consistent set of data, the trends are going to be there generally.
Okay, thanks.
Absolutely. So we'll pick it up very quickly with the exercise. I'm just going to show you quickly. We'll go through one of them. I'm going to stop sharing and I'll put my full screen. 1 second. So we're going to grab this structure here. We're going to plug it into the module here. We'll see how the copy paste goes. Oh, okay, for me it worked. And it may not have worked for some of you. Maybe from PowerPoint versus PDF, it depends. But if you can grab that structure and plug it in, we can run one of these models here. We can check whether it's what its properties are. Oh, this it gave me. Oh, 1 second. Yeah. Oh, you can also copy paste from the Zoom chat as well. This is the example we had earlier. So you just hit run, and I believe this is going to predict that it's a metal. Yep, and you have the full set of properties. You have the bulk modules and the shear modules from the questions. We're not going to run the model, but you can see here it asks for the composition. So this is a nuance for the ASC model. So you have Al, 2 copper atoms, and then manganese. So the composition is going to be AlCu2Mn. All right, so that's the composition you want to type. Just a technicality for those of you running. You don't just want to put the species in, but the actual composition. All right, do we have any questions? If not, we'll pick it right back up with the slides. Okay, so we're going to talk a little bit under the hood from the perspective of the API. So You can imagine that if we wanted to run through thousands of different compounds, it would be very difficult to copy paste from some slides or whatever into the web browser, right? You wouldn't want to do that. What's happening under the hood for this web module is that it's actually taking your inputs and it's submitting it to an API, an application programming interface. So it's actually going to submit your query, your structure, to our server. And then on the server, it's going to queue up all the jobs, right? So all of us are submitting jobs more or less at the same time. So there's going to be some sort of queue. And then it's going to process that calculation and then return the result back to us when we get it. We'll talk about the individual steps there, but the analogy that I'm going to use here is like ordering fast food, right? So if you have an order you want to put in, you want to order a salad or a burger or something, you have your order in mind, you go and submit it to the kitchen, okay? So you go to the kitchen, you submit your order, and he's going to give you a number back. He's going to say you have number 53, and there's 50 something other people waiting, 52 other people waiting. So you wait in line for your order to be finished, and then when they finish with the order, they call out your number, and you go pick up the food. Okay, it's the same analogy here. Okay, so the idea here is you're going to be submitting your order to our API, and you're going to get a response back, which you can continuously query. You can say, "Is my order ready? Is my order ready?" Once your order is ready, you're going to get back the response with the predictions that you're interested in. So we're going to move to the binder exercises. If you can paste them into the chat. And we're going to move there. So it's actually the next slide if you just click on it here. So I'm going to stop share my screen. So if we take this, paste it here. I actually have it opened already. Oh, let's see, 1 second. We paste it. We should each get our own environment. We get something that looks like this. And it'll take a few seconds to load up the environment. Okay. All right, great. I'll give you a few seconds for that to load. Give me a thumbs up if you're able to load it up. Awesome. Okay, great. So for those of you that are familiar with Jupyter Notebooks, this is essentially a Jupyter Notebook, and we have a nice environment within which to run the Jupyter Notebook. So we have some introduction here. I've already talked about a lot of this, but the basic ideas here is that we want to be able to post our query, right? Submit our order for food, and we're going to get back a response that we're going to be able to query to say, when is my order ready? When is my order ready? Okay, so okay, we're gonna go down to where you see the CURL example, to curl example here. So right here, this, as I said, no one needs to be an expert here of coding or terminal or anything like that. We're just gonna be running the bubbles as they are. Basically, on the Mac, you should be able to hit Shift Enter. Actually, on Windows, I don't know what it is, but I hope it's the same thing. So this bubble here, you click inside the bubble. What is the bubble saying? So this is CURL. This is a command for submitting a query to an API. And you see here that this is the endpoint. This is the kitchen, if you will, where we're going to submit our query. And you can see in the query, here we have AFLOW-ML, we have the test postcard. Actually, this here, we're just going to get a structured file. This is the example from the line. We're going to query that from the website. So we have a structure. We're going to save it in our Jupyter Notebook. The next line is actually the submission to the API. So if you look at the query endpoint, the post endpoint, you have here PLMF. So in the query, we're actually submitting which model we want to submit the calculation to. And then we have prediction. And then here, this is basically, we want to submit this structure here to that endpoint. Okay. So we hit enter there. And we should get back a response. We get some sort of ID. It gives us back the model that we submitted it to. And then the endpoint. Okay. This is kind of the number for our food. Okay. So we can take that ID, copy, and we're going to paste it in the next line. You see here where it says insert your task ID. This is your food order number, and you're going to hit enter. Okay, and basically it's this is a query to say, is my prediction, is my order ready? Okay, so we're doing one query because the calculation is very fast. Generally, this is going to return successful very quickly. So We get the full set of results here, and you see at the bottom, we have status equals success. That'll be important for later. But this is basically what's going on under the hood for a web module, and it'll present the results nicely and formatted for you on the web page. Any questions? Okay. So we have here a Python example. Again, no need to understand a lot of the details here, but basically we're just going to be running the cells. I'll go through a quick description. So here we have a set of libraries that we're going to be importing that'll have the functionality that we're interested in using. We set up our server and module here. So this is the endpoints. You see this is familiar from the Jupyter Notebook submissions we had earlier. Here we're going to encode our structure file so that we can submit it to the endpoint. And basically with this line here, we're going to perform that submission to the endpoint. Okay, and then we'll print out our results. So if we hit Shift Enter, we're going to get back our results URL. Okay, so this is the URL we want to query for our order. So we're going to take that, and we're going to copy and paste it. Let's see if I can do that. All right. We're going to copy that. We're going to go down to the next script, and we're going to paste it here where it says results URL. Okay. We have a similar script here, and what it's doing is it's going to submit a request to that endpoint, and it's going to look at the status and see, is it status pending, is it started, failed, or is it success? Okay, since it's already been enough time, that job should already be done, and so you see here we immediately get a response back with the results. Okay, so these are some scripts that you can take. No need to understand all the details now. The point is you have them for running your own scripts in your own workspace. Okay, so we've combined these into another nicer Python script, which is presented here. It basically does in 2 steps. It's a combination of the first two the first 2 Python scripts I showed you. The only difference here is that we have a while loop. Okay, why is that important? Because if we're doing many submissions, there's going to be a queue of jobs, and so when you query is my job done, you might get the answer no, we're still cooking. So we need a while loop that's going to basically say, while the status is incomplete, sleep, wait 10 seconds, and then ask again. Okay, so that's what's going on there. So if we hit enter here, we should be able to, yeah, we should hit enter here. By the way, I'm going to make note of up here. Notice how we break up the server endpoint. We even have the model here, which you know, you could change that out for whatever model you need. So we're going to hit enter there, and depending on who entered when and how the queue looks, you should get the results either immediately or probably in 10 seconds. Yeah, so I got it now. I hope some of you will get it immediately. Just depends on when you submit and how many jobs you submit once you submit it. But our servers can hammer all the time. There's people that are running many different queries, many different predictions. So it just depends on the time of day and what's going on. We have a few exercises. I'll give you 5 minutes to run through them, and then we'll go through them quickly together, another 5 minutes. The first one is very simple. Just convert this VAS4 file format into VAS5. I hope that's pretty obvious from all the slides I've given you earlier. Once you do that, once you convert it into the right format, hit enter so that you save that file into the environment. And then the next question says to retrieve the PLMF properties, and it asks a few questions. What are the bulk and shear modulus values? So you can check that. The next question is change the script. I've already given you some hints. Change the script so that instead of the PLMF model, you run the MFD model. Okay, should be pretty basically one line you have to change, and that's it. It's a very quick exercise. So I'll give you a few minutes to do that, and I'll also take any questions if anyone has them.
There is one in the chat.
Okay. Sure.
If we receive all this information start Python, what's the unit?
Sorry, the units?
Yeah, because there's no like unit.
No, it's a great question.
Yeah.
So the units here, as we
I
provide
know
them,
it's default.
it's the default VAS parameter, excuse me, units. So for bulk and shear modules is gigapascals. For divide temperatures is Kelvin, heat capacity. This should be Kelvin per, I have to look up the unit.
Yeah, I know.
But no,
And
For the, no, it's a good question. I would say that the best reference for that would be the paper. So we have the units there, the paper.
Okay, because it's like basically in the DFT theory, so
Exactly.
all the unit is following.
No, but it's a good question because when you build the models, if you have a lot of different data types,
Right.
different structures, you need to make sure that they're all in the same
Right.
unit,
Yeah,
so.
because
No.
I didn't plug this MD, so the unit is
Right.
mess.
Right. Yes. This is EV per Kelvin, I think it would be for the.
Right.
Yeah, exactly. So we have to take a look. The units might be at the top of the Jupyter notebook, but if they're not, that's actually something very useful to add. So it would be good to add it.
Here's some examples for the first part.
Okay, yeah, there may or may not be good. So I should add that. I'll add that for the next time. Great question. We'll go through the exercises very quickly. Unless anyone has any questions. We'll just go through them very quickly. So to convert this into VAS5, we just added a new line here, MG and O. Okay, any questions there? Hit enter. So you see that it wrote the postcard into the environment. Now this script can grab it. There's no need to change anything here. We just need to run it. And assuming we printed out the postcard correctly, we'll get the prediction there. Okay, so we get the properties back. Bulk and shear moduli are here. They're right at the top, so you can see those values there. And now we're going to change the script so that we can get the vibrational properties back. The line to change is right here, MFD. And we hit enter. And assuming we did everything correctly, we should get a fast prediction back with those properties. Okay? Any questions?
Is there an API that I can
Oh, to understand, so in the API, do we have metadata and all that? These,
Like what kind of metadata we can.
not much. This is very flat. We made it very simple. So the metadata is quite simple. I mean, different models are going to return back just a flat structure with the properties back. So it's not going to be complicated. But yes, if we have a more complicated response, we would need metadata associated with that query. All right, any other questions? If not, I thank you for your time, and we're gonna move on to David Hicks. Let me stop